This video is the third and final part in our unit on collecting data as it pertains to the AP Statistics curriculum, and we will be exploring ways of using studies wisely. Specifically, how do you draw statistically significant results, and how do you conduct studies that would ideally yield statistically significant results? Let's go ahead and take a look at some notes. When members of a sample are chosen at random from a population, we can use the results to make inferences about the overall population, which is a general idea that we have been exploring. You are choosing a sample, and that sample is ideally helping you make a conclusion about the overall population. Now, this concept that we are getting at here is called sampling variability, where different random samples of the same size from the same population produce different estimates. This is something that we would expect to happen. If you have a large population and you are choosing, let's just say your overall population is approximately 1 million individuals, and you are just choosing a sample of, let's say, 100 of them, well, that's not giving you a great spectrum of the entire 1 million. It's just going to be a sample, and that sample is probably going to produce different estimates as you choose different groupings of 100 people. Now, an overall idea related to this is what you can see in the bottom right side of the corner. Let me just get some of this ink off the page, and that would be right here. The larger the random sample, the more precise your information is going to be as it pertains to the overall population. So in this little diagram, we have the percent of red beads that maybe are imperfect. I can't remember where this image came from, but the idea is right here only 20 beads are being used, so the data is a much more spread out normal distribution. But all of a sudden, when 100 beads were used, then the data became a much more tighter version of the data, so you're able to draw a more specific conclusion from those results. Let's take a look at an example. How many likes for Ronaldo? Cristiano Ronaldo is currently the most followed person on Instagram whenever this problem was created. With 640 million followers, how many likes did he get for each Instagram post in 2024 on average? In a random sample of 30 posts, the average number of likes was 6.1 million. Part A, do you think that 6.1 million is the true average number of likes for all Instagram posts made by Ronaldo in 2024? Explain your reasoning. Perhaps pause the video and jot down some thoughts, and I will reveal the answer right now. So we would be surprised if we took a random sample and our estimate was exactly the same as the population average. He has 640 million followers. A random sample of only 30 posts is not going to be a great representation of everything to give us the same as the population average. Different samples will produce different estimates, and this is just an example of sampling variability. So if you were able to take 300 of his posts, maybe that would be a more accurate representation, but 30 posts is a pretty small amount, so this is probably not a good representation of his entire account. Part B, which would be more likely to give an estimate closer to the true average number of likes for all Instagram posts, a random sample of 30 posts or a random sample of 100 posts? And just like what was explained on the previous slide, the more people, the more individuals in the random sample, the closer your information is going to get. A SRS, a simple random sample, that will be used again later. A simple random sample of 100 posts will give an estimate closer to the true average number. A larger sample will produce a more precise estimate with less variability, because again, that is the point. The more individuals you are including in the sample, the less likelihood that you're going to have extreme variance. Here is the beginning of a very, very important concept that we are going to get to regarding things becoming statistically significant. So please listen carefully. We are starting up here in the upper corner. There are two ways to explain why the average response for one sample is different from another, because as it was just talked about, different samples produce different estimates. This is called sampling variability, and I'll assume the subtitle will take care of that. So how do we account for sampling variability? What do we think about? There are two things that you consider in order to justify that sampling variability. One thing is, the treatment that you are imposing does not have a different effect for the groups, and the difference in the response happened by simple chance variation in how the individuals were randomly assigned. Now, that's going to sound like a lot, and we are going to do an example to explore that idea right there, but the basic idea in this situation, to account for your sampling variability, it might just be because your individuals were randomly assigned. There might not actually be any impact that the treatment is having on individuals. You might just be seeing a difference because that's how people are. As a quick example of this, if you were to do a study on how caffeine affects different individuals, you would have two groups. One group, we can just quickly represent this, one group would be getting caffeine and the other group would be getting no caffeine. And then you would measure the results results of how perhaps their heart rate was increasing in the caffeine group, and you're going to be getting some data. But then random assignment means if you took all the people in these groups and then you shuffled them around, would you get the same result or would the results be different? And when you think about caffeine, well, there's other things that would affect how a person reacts. What if they are in really great shape and their body processes caffeine really well? Or maybe they're in great shape, but their body just doesn't happen to process caffeine very well. What if somebody in this study was already pretty involved with caffeine, so their body is very much used to it, meaning their body might not react in the same way than someone who doesn't have caffeine? What I'm getting at is an example like this with caffeine and no caffeine, you might get a difference in the response where you could very well think, oh, well, caffeine is certainly going to affect people, but it might not just be because caffeine. It might be because the people who were chosen in this group just happen to be more susceptible to caffeine, and you don't know that for sure. So sometimes when you see a difference in the response, it might just be because that's how people were randomly assigned to the group and the treatment isn't really proving anything. And we will explore that in a moment, but that's probably the most important idea that will be talked about in this video. So let me just clear this extra ink. And the other reason why you might see sampling variability is the treatment actually does cause a difference. And that makes sense, of course. You are very much looking for that to happen. This starts getting us to the idea, if you have taken another statistics course before, we have our null hypothesis and then the hypothesis we're trying to prove. That's where all of this information is now going to go, but we will get into it in a later section. So let's take a look at an example right here just to sort of understand the main idea of how to, again, make sense of sampling variability. So this study right up here at the top, I condensed the text, so I will just explain it right now. What was examined was the there's a random assignment of students into groups that would be driving on the road. And some of the groups had people where there was a passenger in the car talking to the driver. And then in some of the groups, there was no passenger and the driver was talking on their cell phone. So the study was trying to explore if the driver would remember to stop at a rest area. So they were told, you got to stop at this rest area, but you're going to have a passenger in the car, and then some of you are going to have just your phone and you're going to be talking to somebody. And the study was exploring, did people remember to stop at a rest area when they had a passenger in the car versus when they were just talking on the phone? So you can see the data in the table right there. And part A, what's the difference in the proportion of passengers minus the cell phone users for those that stopped at the rest area? So I will just show you the result of that right now. You just have to do the calculation of 12 over 24 and 21 over 24. So we can see that those who stopped at the rest area, there were 12 of them that were using their phones, and 12 of them out of the 24 stopped at the rest area. Or 12 of the people who were on their phone stopped at the rest area. And then the passengers who were, or the drivers who had a passenger, there were 21 of them that happened to stop at the rest area out of the 24 that had a passenger in the car. So what we're seeing is way more people remembered to stop at the rest area when they had a passenger in the car. Now, that's just not enough. We need to see if this is going to be statistically significant. So you start by finding the proportion of people who successfully stopped with a passenger in their car versus those who stopped with only being on their phone. So that would be the two fractions you see over here, 21 over 24, and you would just subtract 12 over 24. We're just finding the difference. So you are subtracting those two fractions. And when you do that work correctly, you get 0.375. So that is the difference in the amount of passengers that, or the amount of drivers that stopped with a passenger and those who stopped with being on their phone, suggesting that the phone is more of a distraction and the passenger allows you to be more aware of your surroundings so that you actually stop. That is part A. Hopefully that makes sense. Back things up in the video if you need to hear that again. Now let's talk about part B, easily the most important concept of the entire video. Are these results statistically significant? So here is how you make that determination. You will always be given the following scenario. This study was done, so you have the information right here, and then the study is now replicated. So that's where software comes into play. This study has now a replication of 100 times where the people were randomly assigned to being in different groups. So what I'm getting at is this. What you're seeing in this table right now are the 24 people that were assigned to have only their phone while driving, and then the 24 people who were assigned to have a passenger. Those were two groups. And I'm not going to put all 12 X's in each of these groups. I will just, let me just use a different color right here. Now you're going to do 100 simulated treatments of this idea, where in some of those treatments, you're going to be getting some of the people who were originally in one category now appearing in the other category, meaning they did not have a passenger in their car and now they do. And this replication happened 100 times, and it's just done by software. You already know the results of what each of these black and blue X people are going to do. We are now just randomly assigning them to see if those results are going to be what is called statistically significant. And here is how you do that mathematically. Let me just get the extra ink off the page. All right, so let's take a look. Starting down right here. A difference of 0.375 did not occur at all when many of the simulated trials did occur. So when you look up here at the normal distribution, that's the other thing. When you are doing your simulated differences, you're trying to see if the result of 0.375 is normal, is typical. And this normal distribution, this bell curve, if you notice right here at the end, that says 0.3, and we have a difference of 0.375. These are all the differences of those 100 studies represented in this normal distribution. And since 0.375 didn't even happen once in any of the other randomized software-driven samples, we can definitely say this is statistically significant. And if there is something to additionally write down on your paper, it would be this piece right here. The results happening under 5% of the time are considered statistically significant, less than 5% of the time. So you have ideally seen a normal distribution if you are watching this video right now. And where this idea is going, it relates to, well, that's a really bad bell curve. There we go. It relates to the empirical rule, where you have 67% of your data within one standard deviation, and then 95% of your data is within two standard deviations. Less than 5% of the time would be the very, very upper tail of your normal distribution. And if you have a value that is existing all the way in that upper tail, then that value is not happening very often. It is statistically significant, as we say, and it's where the result happens under 5% of the time. Now, at the worst case scenario, if me explaining all of this right now, you don't really understand what's going on, that's okay, because these problems are designed in a very procedural manner. So as long as you just follow this procedure and you listen to what I tell you to look for, you will be able to get these right every single time. So let's do an example where perhaps you should pause the video, try to do it on your own, and jump back to this example right here in order to help guide you so that you could be successful on this practice problem. So here we go. Is yawning contagious? According to the popular TV show Mythbusters, the answer is yes. The Mythbusters team conducted an experiment involving 50 subjects. Each subject was placed in a booth for an extended period of time and monitored by a hidden camera. 34 subjects were given a yawn seed by one of the experimenters. That is, the experimenter yawned in the subject's presence before leaving the room. And sometimes that's what happens. You see somebody yawn, so you in turn yawn. That is what the yawn seed idea is talked about here. The remaining 16 subjects were given no yawn seed. So notice it's not a 25-25 person split. It is 34-16. What happened in the experiment? The table below shows the results. So very much like the example that was on the previous page. Part A, and this is where you should pause the video and give it a shot. Calculate the difference between yawn seed giving a yawn or no yawn seed giving a yawn. So you're going to want to be looking in the yes column right there, and I will show you those results right now. So you have 10 out of 34 people who got the yawn seed and also yawned, and then 4 out of 16 people who still yawned without getting the yawn seed. So you calculate both of your proportions and you subtract them and you get 0.04, and that is the difference in the two proportions. That's all you had to do for part A. Here we go with part B. A total of 100 trials of a simulation were performed to see what differences in proportions would occur due only to chance variation in random assignment, assuming that the yawn seed doesn't affect whether a subject actually yawns. So that's the key thing right there. We are now looking at our null hypothesis, but that's coming up in a later chapter. The situation where nothing is affected, or the yawning is not affected by the yawn seed, your null hypothesis. That is, 14 yawners and 36 non-yawners were randomly assigned to groups of 34 and 16. So this is now going back to what was talked about on the previous slide. You already have the data collected, but now you are deciding if chance variation gave you this difference of 0.04, or if chance variation is why the results were what they were. We're trying to see, does a yawn seed actually influence you, or did this result happen just because certain people were assigned to different groups? Maybe somebody was more tired on the day this study was being done, so they were more likely to yawn. Or maybe somebody just naturally doesn't need a lot of sleep, so they're not generally tired. This is chance variation in random assignment. So, part B, there are 5 dots at 0.23. Explain what these dots mean. And there they are highlighted right there. And the dots would mean a very simple statement. Assuming that the yawn seed doesn't affect yawning, so that is your null hypothesis idea that doesn't affect yawning, there are 5 simulations where the difference in proportion of people who yawn is 0.23. You're literally just counting the dots that are there, and you are reiterating the context of what the study was looking for. And then lastly, part C. Use the results of the simulation where now software gave us all of these different results, all of these different proportions. We got 0.04 from the main iteration of this study. And we are now seeing that software has given us what does look to be a normal distribution. So we are trying to determine if these results are statistically significant. And here we go. So because a difference of 0.04 or more happened 56% of the time. That's what you had to observe from this table. That is unfortunately very tiny, but I'll highlight it right there. 0.04 was a very, very small number right there, but there were a whole lot of results from the randomization that were at least 0.04 or more as a difference of between the proportions. So because there were so many 0.04 differences that happened in the study, that is way more than 5% of the time. So this is not statistically significant information. This result, this proportion happened very, very often when the individuals in this study were reshuffled into the different groups. So if we're getting the same proportion, but everyone's just being reshuffled around, then that means the treatment isn't exactly causing, or we would not assume that the treatment is causing a significant impact on whether or not somebody is going to yawn. Whereas in the previous study, we looked at using your phone versus talking to somebody might be statistically significant in your attention span while on the road. Hopefully this part makes sense, and definitely rewind and replay it again. If it does not, you will be seeing more instances of things being statistically significant in some of the practice material to come. Let's look at one more idea and then we'll be out of here. The scope of inference. So we have now talked about 2 different ideas in this entire chapter on collecting data. We have the random selection of individuals, and when you randomly select individuals, you are able to make inferences about the entire population. Whereas if you are randomly assigning individuals into groups, now you're going to be making inferences about a cause and effect relationship. These are 2 different ideas that will all vary as you explore things that you are collecting data and trying to make an experiment on. So to help you understand the different scenarios that you will be in, we are down here in this table, which is just showing you the interaction of both of these moments happening or not happening. For instance, if you are randomly selecting people, so you're randomly selecting people that are going to go into a study, and you are randomly assigning those people into groups, that means you are going to be able to make inferences about the population. You randomly selected people. Good job. You used a simple random sample to randomly select individuals. And since you are also randomly assigning them to groups, then good job. Your random assignment to groups is going to allow you to draw cause and effect relationships. This is just a table to help you make sense of what you are using as your sampling choice, the way you are collecting your data, and what conclusions you're able to make. Is it a population-based conclusion? Is it a cause and effect-based conclusion? So let's just look at another one going down right here. Let's say you are not randomly selecting individuals. So that means they probably volunteered to be in your study. And once you collect your volunteers, you then randomly assign them into groups. Well, okay, since you're randomly assigning them to groups, that means you're going to be allowed to make a cause and effect determination at the end of your study. You can make that inference because you randomly assigned people to groups. It's okay that they were volunteers. You just can't make a conclusion about the population because maybe there is bias in why those volunteers actually did choose to be in the study. Maybe there is some underlying factor that they all share in common, which would skew your data. But since you at least took your volunteers and put them into randomized groups, then you can apply a treatment and draw some cause and effect relationship. And then the other 2 situations are just the opposites of what I just referenced. So I will let you read read and highlight that on your own. One more practice problem. Silence is golden. Many students insist that they study better when listening to music. A teacher doubts this claim and suspects that listening to music hurts the academic performance. The teacher selects a random sample of 30 students from the school to participate. Each of the selected students is asked whether he or she studies while listening to music. And then their GPAs at the end of the semester were recorded. Key thing to note, it was a random sample, not a random assignment. The results, students who listened to music while studying generally had lower GPAs than students who didn't listen to music. What conclusions can we draw from the study? Are we able to talk about the population? Are we able to do a cause and effect inference statement? So pause the video, maybe flip back to the previous slide, and here we go. Since there was a random selection, the results apply to the students similar to those in the study. We are able to draw conclusions about the population, which would be the students in the school, because again, we used random selection. There was no random assignment into groups. So we are not doing a treatment imposed on groups. We were just looking at students who were randomly chosen. So we cannot conclude any cause and effect relationship here because we did not do a randomized assignment of people into groups. We just took students in general as a random sample. So if you're not declaring that you are randomly assigning individuals into groups, then you are not able to make a cause and effect justification at the end of your study. All right, I hope this gave you a good idea of what the procedures of collecting data and the various ways of doing it all involve. Drop a comment if you have any questions, and I will see you next time.